Hello, in this video we're going to see how we can simulate the national grid system, and this is often done right at the end of the electromagnetic induction topic when we've covered transformers, AC electricity and generators, and it's a very useful topic to try to set the context of all the basic theory we've done. To do this as a class demonstration we need the following equipment. So a power supply such as the Irwin Powerbase S10 here, and we're going to use the 0 to AC yellow connections here. We need two 12-volt filament lamps on holders, selection of 4mm leads, and we need the simulation of the national grid. These units are identical, they've got transformers inside, but we're going to use this one as a step-up transformer and this one as a step-down transformer. We also have some model pylons, and this pair of special connections with shrouded sockets there and insulated cables represents the national grid cables going across the countryside from the power station to the towns. If we're going to look at the measurements of the national grid in terms of current and voltage, then these two IPC digital meters, this voltmeter which measures up to 20 volts AC and this ammeter measures up to 10 amps AC, can be useful if we want to do some measurements with the students. So the first stage is to connect a lamp up to the power station. So imagine that this is a lamp in your house and you live right next door to the power station. So if we switch on the power supply and gradually bring this up to around 12 volts, the lamp glows very nicely. Switch that off and then just add one section of the transformer unit. We're not going to use a transformer here, we're just going to show what it's like to connect a lamp in parallel with it 100 miles away in the town. So we need to use these special connections now, and they're a bit fiddly to connect for a very good reason. They're shrouded because at some point they'll be taking 240 volts when we use a step-up one. But this moment we're not going to do any transformers at all. We're just going to create a parallel circuit like so. Okay, now the graphic in this video shows you that all I've done now is connect this lamp in parallel with this lamp and the power supply, but we now have the idea that this is a 100-mile national grid cable stretching across the countryside from the power station to the tower. Now again, switch that on. Lamp is glowing brightly as before, but as you'll see with the close-up shot of this lamp, it's glowing dimly. So it's in parallel with this one, so why is that? Well, when the electrical energy is passed down through these cables, the cables themselves have got resistance and potential difference is lost in here, so we don't get the full 12 volts across here. We just get a tiny fraction of the 12 volts there, and the lamp isn't bright enough. At this setting of 12 volts, I can feel that these conductors inside the plastic insulation are slightly warm, and that's where the energy loss is happening. So imagine this in the context of a national power distribution. Clearly, we can't just have consumers close to the power station. We need them all over. So that's where the step-up and step-down transformers come in. So switching off the power supply, we now remove these connections and we plug them into what will be your right-hand socket there, which is labelled high voltage. Now it is important you don't get these connections mixed up. We've got to connect the high voltage, this one, to the high voltage on this one. what's happening now? Well, the circuit's a little more complicated, as you can see from the graphic. We've now added a step-up transformer in this box here, which is taking the 12-volt AC and stepping it up to 240 volts AC. So these cables now have got a much higher potential than 240 volts across them. And that's taken across the countryside to the town, where they meet this unit here, identical to that, except it's working in reverse. This is now a step-down transformer, and it's taking the 240 volts AC and taking it back down again to 12 volts, so it can be safely used in our homes and for this lamp here. Now, if we switch on again, you can now see that both lamps are lit brightly, and the power loss in these cables is much less. And I can feel now they're cooler because the 240 volts across these cables is now carrying a much smaller current. And as we'll see from the second video, where we look at the more advanced use of the formulas, we can show mathematically why that is. So just to finish, a note of safety, do make sure that these cables aren't damaged, and technicians know how to connect these up correctly. You could damage the units, and you could even get more electric shock if these were damaged in any way. So do check the insulation, and you know how to do that. We do have, finally, a couple of model pylons, which represent, the distribution across the countryside. And if you look at our online worksheet on the CPD Science link, there are also some very informative videos showing how the national grid is built in the United Kingdom, showing you substations in various locations, and a little more detail if you want to do a bit of enrichment on the national grid.